Take a plane and draw n lines on it. No two lines are parallel, and no three lines pass through the same point. Here's the question. How many regions do these lines cut the plane into? One line gives two regions. A second line crosses it, and now we have 4. A third line crosses both, and we're at 7. Now watch the fourth. The classic way to solve this is recursion. Each new line crosses every old line, so it passes through a bunch of existing regions and splits each one it touches in 2. Count carefully, and line number n plus 1 adds n plus 1 new regions. And that's actually enough. Unroll the recursion, and you get a closed form answer. It works. But this video is about a different proof. One that's not just cleaner, but tells us something deeper about the answer. The extremal principle is one of many principles for counting problems. I first found it in Arthur Engel's book, Problem-Solving Strategies. It says, look at the extreme object. The largest, the smallest, the deepest. So to count our regions, what's the extreme thing we can count? The deepest point of a region. Let's try counting those. So here's the plan. We'll count the regions in 2 buckets. Some regions have a deepest point, a lowest corner where the region bottoms out. The rest have no deepest point because they keep going down forever off the bottom of the plane. Count each bucket separately, then add. But wait. Could a region land in neither bucket? Yes, if a line were perfectly horizontal, a region could bottom out on a flat edge. A whole edge of deepest points, not one. But we have finitely many lines, so rotate the picture slightly until no line is horizontal. Nothing changes, and the edge case is gone. First bucket. How many regions have a deepest point? Here's the trick. Don't count the regions. Count the intersection points. Pick any point where 2 lines cross and zoom in. The 2 lines make 4 wedges, and exactly one of them opens upward. The region sitting in that wedge has this exact point as its deepest, and that works at every intersection point. Each one pins down exactly one region, and every deepest point sits on one of them. That's a 1-to-1 correspondence. If you can't count the things, count their partners. And intersection points are easy. With n lines, that's n, choose 2. Second bucket, the regions that run off the bottom forever. Drop a horizontal line far below everything. Our n lines each punch through it at one point, cutting it into segments. Each segment sits inside exactly one runaway region, one segment, one region. So the question becomes, how many segments do you get when a line is cut by n points? N plus 1, of course. But notice what we just asked. A line cut by n points into how many pieces? That's our original problem, 1 dimension down. And the same proof works there, too. Each point is the deepest end of exactly one piece. That's n, choose 1, plus a single piece that runs off forever. That's 1 more. So the full answer stacks up. N, choose 2, plus n, choose 1, plus 1. Notice what happened. The plane problem contained the line problem, 1 dimension down. But the same machine runs the other way too, upward. So slice 3-dimensional space with n planes. No 2 parallel, no 3 sharing a line. How many regions now? Same 2 moves. A region's lowest point sits where 3 planes meet. That's n, choose 3. For the regions that fall off the bottom forever, drop a plane below. Our 3D planes divided into 2D regions, and each 2D region matches exactly one runaway region. So we've reduced it to 2D. Count the regions n lines make. Stack them, n choose 3, plus the 2D answer. That's the real payoff of this proof. The recursion hands you a number. The extremal principle shows you what the number is made of. Two tools did all the work. Find the extreme object, then build a one-to-one correspondence. And those two tools solve a lot more problems than this one. If you want more of them, Engel's book is full of them. Thanks for watching.